Yes, we can start now. Sorry for the technical
No
issue.
problem. Yeah, thank you. Okay, so thank you very much. So, and first of all, so I'd like to thank the organizers for giving me opportunity to talk this Majorana-Raychaudhuri seminar. So, I am a postdoc working at Kavli IPMU at University of Tokyo, and today I'd like to talk about our recent studies on the implications of the measurement of cosmic birefringence for the parity biorhythm physics. Okay, so let me start. Okay, so first of all, so let me introduce a brief introduction of what is cosmic birefringence. The cosmic birefringence is like a parity biorhythm phenomenon by a cosmic birefringent material. So it means, so now we can assume the pseudoscalar field, such as the axion field, coupled to the electromagnetic field, so just like this. So in the presence of this kind of parity-vibrating interactions, and then when we, so write down the dispersion relation, the equation motion for the two circular polarized photons, left-handed and right-handed. So we have this expression of the frequency is like phase velocities of the two polarized HT modes, and as usual, it's both have the same phase velocity, but in the presence of the cosmological background in this case of the axion field, it deviates from unity. The magnitude of correction is the same between two HT modes, but the sign is the opposite to each other. So what happens? So let's consider the linear polarization. So linear polarization is given by the combination of the two circular polarized photons. So, but if one is faster than the other, the combined linear polarization is slightly tilted. So it's caused by this axion pseudoscalar field photon interactions. So that's why. So it leads to the rotation effect of the linear polarization direction. And actually, so we are interested in so how this kind of a birefringence effect might be observable. So we look at the CMB polarization map. So the CMB polarization is emitted provided by the Thomson scattering processes. Then we have two kinds of polarization modes. One is the CMBE mode. The other is CMBB mode. And so when we consider the parity feature of these two modes, so what happens? So, but before talking that, so yeah, the motivation is like, so the of CMB physics is like to test the CMB so angular power spectra. So we have a temperature, anisotropy, and E mode, B mode power spectrum. And then so this figure shows the measured several CMB power spectra. So the power spectra of temperature and E mode have been precisely measured, but the B mode is still dominated by instrumental noise. It's very small, especially from the primordial inflationary B mode. And so now we be just developing and improving to test this primordial B mode signature in the next decades CMB observatories, such as Simon's Observatory or satellite light bar mission. Okay, so this is the background. Then, yeah, so let me go back to the what happens when we consider the parity transformation. So we have E mode and B mode. And when we do the parity transformation, so it turns out to be just like this. The, as a polarization pattern, the E mode doesn't change its shape, but the B mode changes its kind of orientation. So, and we have, due to this property, the E mode is a parity even, and B mode is parity odd under the parity transformation. And we have two kinds of power spectra. So one is a parity even, that temperature anisotropy, it's TT and EE and BB and TE. So there are parity even, and so it doesn't change under the parity transformation. And actually, so we know the parity invariant theory, so we can naively assume so our universe is governed by parity conserving theory, and actually this kind of a parity even spectra has been well measured. But on the other hand, we have a parity odd angular power spectra. It's a cross correlation between T and B or E and B mode. And then, as usual, under the parity conserving theory, so it doesn't predict this kind of a parity odd correlation function. But if we could measure this kind of stuff, see, it might be a hint for parity violating physics. And actually, it's not well measured up to now. So, so in the presence of the parity violating interaction, such as axion photon interaction, it provides the EB correlation function. So this figure shows okay, so in the presence of action photon interaction, the original polarization plane is slightly rotating, and then we observe such a rotation effect with the angle of beta. So the cosmic birefringence, such a cosmic birefringence converts the original E and B mode as the following rotation matrix. And we are observing this mixing E and B mode. So then we can produce a parity odd EB correlation, just like this. So it's given by the product of a periodic function of rotation angle beta times our known intrinsic CMB, EE, and BB angular power spectra. And we may have another contribution from a primordial intrinsic EB correlation function. But so in this talk, we assume it's 0. So in our universe, so we don't assume any parity violating stuff producing EB. And so we assume only a late time for some mechanisms. So it produced this EB correlation function. And by the way, this expression, so we assume beta is assumed to be constant from the last scattering surface to present. So, and recently, so we may have a big news. So we might measure the hint of the parity violating physics. So it's a measurement of the cosmic birefringence. So recently, a non-zero isotropic, it's an overall rotation of the polarization CMB. It's called the isotropic cosmic birefringence angle, was reported by the Planck data at first. So its significance is around the 2.4 sigma. And then the next studies improved this significance. And the latest joint analysis of the Planck and double map tells us, so it's over 3 sigma detection of this isotropic cosmic birefringence angle by measuring the EB power spectrum separating from the systematic miscalibration angle. So if it's finally confirmed in the next decades, so it's definitely a hint for a new physics, parity violating physics, such as axions. And so how to explain such a isotropic cosmic birefringence? So in the previous slide, I showed the linear polarization rotation is potentially caused by this kind of axion and chance-Simons photons coupling. It differentiates the phase velocities between two circular polarized photons, and assuming this is small, we can expand it just like this. Then the beta, the rotation angle of the cosmic birefringence, is given by the time integration of phase velocities. So the difference between two angular frequency left and right handed. Then it's given by the time integration of the speed of axion field. So very simple. So it's given by the product of axion photon coupling times and the field displacement of axion field between the observing points and the emission point of CMB polarizations. So, and so to evaluate the magnitude of isotropic cosmic birefringence, it's really related with the time evolution of the axion background. So, okay, in this case, let me explain the simplest toy model. So it's a white square potential. And we have the equation of motion for the background action of field obeying a correct equation in the history of the universe. And at first, assuming, so now mass is super small. And first, the Hubble is dominant. The Hubble friction is dominant, and it's frozen on the slope of potential. But Hubble decreases in time. Then at some point, so these terms become comparable, and mass term becomes dominant. Then the action field starts to oscillate on the potential minimum. And this figure shows such a behavior with respect to the several mass hierarchies, mass ranges. So, and this gray band shows time domain when the CMB polarizations was emitted. So this is correspond to the recombination epoch. Then this correspond to the cosmic reionization epoch mainly. So, and the point is like to evaluate this beta, we have to evaluate the field displacement of action field between at present. So sorry, but this is a x-axis is a logarithmic scale, but so this far left side is almost at present, we can assume. So it means so for certain mass range, so we just evaluate the field difference between this point and this emission point of CMB polarization. So and depending on the mass scale, especially for heavier mass range, it starts to oscillate the potential earlier in the earlier history of the universe. On the other hand, for lower mass range, so it's still frozen during the CMB period, but then it starts to oscillate at a later time. So that's why, depending on the mass scale of action field, we have to so to explain the current measured by beta, so we can constrain the magnitude of this action of coupling. So that's a point. So then this is a constraint of the parameter space of action coupling with respect to the axial mass from the measurement of isotropic cosmic birefringence. So especially this figure shows for axial mass comparable or lighter than this Hubble parameter scale at current Hubble parameter corresponding to the 10 to the minus 33 electron volts. So this parameter region shows axion is still fixed on the potential and behave as a dynamical dark energy. And then due to the slow roll motion of dark energy, the field excursion is approximately given by the proportional to the mass and the field value over Hubble parameters. Then the beta is given by this proportionality expression. Then we can plot these constraints. So, and that's why the cosmic birefringence measurement potentially cause access to the parameter range of axion as dynamical dark energy. So, but to explain the action's dark energy, so it's known that there's a conventional issue. So it means, so I assume that mass, the quadratic potential, but originally, so it might be generic to consider the cosine type potential. So from the axion. So, and to explain the action's dark energy, so we need nearly flat potential correspond to the very long range of this decay constant scale. So, and then to meet the slow roll conditions, so it corresponds to the constraints on the equation of state for dark energy, it requires the decay constant is much greater than Planck scale. So, but so it's known that from the high energy physics point of view, so in control setup of this near flatness of the potential, I mean, so this decay constant should be super Planckian. So no, sorry, sub Planckian scale. So it should not be super Planckian. So or we may avoid it by layering on the fine tuning issue. So like putting on the action field on the top of hair, close the top of hair, but so it's just the fine tuning issue. So, and then to more or less resolve this kind of stuff, so there are a couple of candidates, but so let me, for instance, explain it by another mechanism of axial monodromy. So the axial monodromy is known as a kind of a effect from the actions potentials from wrapped brains. So we consider the DBI action for the brain, and assuming the action field originally it's a kind of a Ramon field or something compactified on this directions manifold. So we have this kind of it's a bit sorry, many model parameters, but DBI potential. But for large field limit, it's simply approximate to the linear potential. So, and so it does not have the original kind of a shift symmetry any longer. But owing to this mechanism, so the potential energy, yeah, I know. So the typical cosine potential is bounded from above, but this is not bounded. So it means even if the action has originally the periodic symmetry, but the energy is not bounded from above, so we can go up and up, keep on doing. So and then so even if the original scale is a sub-Planckian, so we can extend action field value to the periodic scale and effectively go beyond the Planck scale. And this mechanism might explain the measured cosmic birefringence. So that's a motivation of this scenario. So and so we just suggested to explain isotropic cosmic birefringence. So from monodromic action dark energy, we just constrain the parameter space of a linear potential of action. So this is a constraint of the action from coupling with respect to the potential slope, assuming the the beta is fixed to the around the 0.3 degree. It's a measured value. So and then cosmic birefringence can constrain on these parameter regions, and especially we can explain the cosmic birefringence by the following range of decay constant normalized by the anomaly coefficient. But assuming it's around the order 1, so it's around the sub-Planckian and Gato scale. So by the way, this Chandra means constraint of the astrophysical observations of the action photoconversion effects by X-ray. And this Planck means constraint of the equation states. So and this is a survival region. Okay. So and for action field with a heavier mass range, it's also possible to explain the isotropic cosmic birefringence. But the thing is a bit complicated than the action as dark energy. So it's because for these mass ranges, so especially this figure shows for action mass ranges above the 10 to the minus 33, so 32, 31, 30, minus 28. So it starts to oscillate at certain time of the history of the universe, especially for action or certain mass range, it starts to oscillate, just correspond to the this emission time interval. So we generically have to numerically solve the Boltzmann equation of the polarizations coupled to this action of coupling. Then, depending on the mass ranges, it predicts a unique spectral shape of a EB correlation function. So in the previous studies, especially axion behavior of dark energy, it predicts a constant rotation beta. So, but in that case, the beta, the rotation angle itself, that depend on the time in the history of the universe. So that's why, so depending on what time it starts oscillates, so it provides a unique signature, for instance, such as a bump, a structure of a cosmic reionization epoch, for instance. So that might be a unique signature of the EB power spectrum. So, and related with this study, so there are several constraints on the such a heavy actions in the scenario of the dark energy model, or the use of gravitational lensing, or polarized Snellius effect, or the formation of the topological defects such as domain world networks. So there are the recent studies on the giving implications of isotropic cosmic birefringence from the point of new physics. So, but okay, so let me ask the question, naive question. So now, so I think most of the studies related with this measured isotropic cosmic birefringence is from the motivation of actions or new physics. But so why new physics is necessary, or why not our known physics, in standard model of particle physics? So if it's possible to explain it without introducing any new field, new light field, new physics, that might be, so that might be natural. So it's like we can learn it from the, for instance, the lesson of William Ockham. So all things being equal, the simplest solution would be nice. So, but what happens in the case of isotropic cosmic birefringence? And for the rest of this talk, so I'd like to show why axiom or new physics is important to explain this cosmic birefringence. Okay. So other than such a axiom, axiom effect, so we know the polarization rotation effect in the context of standard model. So it's a Faraday rotation. Especially we are interested in the Faraday rotation effect in CMB. So it's a polarization rotation effect from the, in that case, a large scale magnetic field, cosmological magnetic field, and free electron. So its rotation angle is given by the this rotation measure functions in the integration along the line sides in the presence of electron density and magnetic field. And also, it depends on the wavelength of the photon. So, and in that case, so so we are interested in the overall rotation, isotropic cosmic birefringence. That's why. So if there is a large scale primordial magnetic field, so it could provide so the EB correlation function for our interest. And actually, in the study of primordial magnetic field genesis, so there's upper limit on the primordial magnetic field from the CME observations. It's less than around the 1 nanogauss scale. And the other case is it might be a bit complicated, but so in the presence of cosmic neutron background, it might also predict cosmic birefringence. So as of course, the neutron doesn't couple to the photon tree level, but so there are the loop interactions, loop of the electron of the bosons, just like this. The neutron anti-neutron background asymmetry could provide a difference of photon propagations between two HTs. So the computing diagram is a bit complicated, but as a result, we get the photon's rotation angle per some cosmological length given by these functions. So it depends on the photon's angular frequency and neutrino anti-neutrino asymmetry of the number densities. So by the way, so now we are looking at the photon's energy much smaller than the mass scale of the double boson. And in the case of off-shell case, so in plasma, so we also obtain the cosmic, the birefringence angle given by the plasma frequency and the neutrino anti-neutrino asymmetries. And this, so asymmetry is given by this degeneracy parameter. Then this is much less than the order unity from the constraint of the Big Bang nucleosynthesis or something like that. So, by the way, okay, all of these effects, so how much magnitude of rotation angle they predict. So this figure shows, okay, so this large phi is normalized of birefringence angle per the Hubble scale. So, and the x-axis is photon frequency, and the y-axis is this phi. The unit is radian, not degree. So that's why to explain this current measured value of beta in terms of the radian, it's around 10 to the minus 3. Effectively 10 to the minus 2 radian would be necessary. But, so we can see that those predictions is very small. So the order of 10 to the minus 40 or 10 to the minus 60 for lower photons frequency, especially the cosmic microwave background frequency regime. So it's very small, at least from the neutron gas effect in vacuum or in the plasma. Potentially, the Faraday rotation effect in the galactic magnetic field might reach our interest parameter regime. But so there is another observational fact. So it's like okay, so from the Planck data analysis, there's a constraint on the frequency dependence of the birefringence angle. So we can characterize this rotation angle into the amplitude and the frequency dependence characterized by this index. So this figure shows the constraints on the frequency-dependent cosmic birefringence angle. And actually, for now, for nearly full sky measurement, the beta is around 0.3 degree, and this spectral index is a non-consistent. So at least at observation level, errors level, so it's consistent with the frequency-independent cosmic birefringence angle. So that's why the Faraday rotation predicts frequency-dependent cosmic birefringence angle. That's why, so we can say from this measurement, so Faraday rotation effect would be inconsistent to explain the isotropic cosmic birefringence. So, okay, so to be summarized, so now we saw a couple of examples from the standard model producing a cosmic birefringence angle, but so it's fun to be failed to explain the current measured value. So, and but it is still impossible to explain the birefringence angle in our known fields. So, I mean, so we may need to consider beyond standard model, but we may not need a new field, such as axion. So it means so we can effectively disrupt the all relevant cases of the kind of beyond standard model, but the effective history of standard model by our known field. So it's like by considering the SMEFT, so the effective history of standard model. So, okay, so before going to this, so let me explain. So as a tool to describe it, it's a effective Lagrangian approach. So I showed in the previous slide the photon-neutron loop interactions, just like this. And so computing it straightforwardly, the scattering process will be complicated, but effectively, so we can characterize them by the Lagrangians, effective Lagrangian. So it means for low energy, so we are looking at the photons, low energy photons, smaller than the mass scale of electron and the boson. It means so we can localize this process. Then above interactions can be described by the following integrated out operators. So it's a bit, it's a higher dimension operators. It's a bit complicated, but the point is like by rewriting it, so we can lead to a list of parity violating operator form, just like this. So this is an operator, and this is a Chern-Simons FF tilde. So so how to do that in the context of isotropic cosmic birefringence? So to explain this birefringence, we need to consider these Lagrangians, especially on a cosmological background. So we just do the, so we just do the average value of these operators. Then the rotation angle is given by its field displacement. So it's given by this time integration, and it's given by the this cosmological background operators at present and at last scattering surface. So for instance, if this operator includes this kind of a derivative factor, so it turns out to the frequency dependence of the photons. So we can judge, oh, it's not consistent because current measured value favors frequency independence. So so by doing that, so we can more or less categorize what kind of operator would be relevant to explain the cosmic birefringence effect. So, and about the SMEFT or low energy effective theory, so it's LEFT. So, but yeah, again, so this is not standard model cell, so it's a beyond standard model, by the way. But so it includes operators from all of the standard model fields, and which respects the our known gauge symmetries. By the way, the LEFT, it's a EFT below the electroweak breaking. Okay, that's why the symmetry is a bit reduced, just like this. So then we assume no undiscovered light particles, such as axion, exist. So we just need our known standard model fields. So, okay, so first, I'd like to show our result. So only a Chern-Simons type effective operator, this kind of operator, and scalar, Lorentz scalar operator can produce a frequency-independent isotropic cosmic birefringence. But, so in our work, so in this paper, we showed the no of such effective operator leads to the desired birefringence angle. Okay, let me explain it. So the Chern-Simons type scalar operator is given by this kind of a form. And then, so depending on the number of operator species, and then dimension of the operators, higher dimension operators. And then this is Lorentz scalar operators. It's a singlet for the standard model symmetry. Then, respecting these, we can list up all possible operators of each dimension. So, and mainly there are these building blocks to characterize these operators. For lowest dimension, 1, it's a Higgs field and covariant derivative. And the next 3/2 dimension, it's a standard model fermion. Then dimension 2 is a standard model field strength tensor. So by using these blocks, we can construct this operator form. And let's do it from the lowest dimension, so dimension 6. So we can see that. So it's reduced to this Higgs square or covariant derivative squares. But by using the equation motion and so avoiding frequency dependence of operators, we find that the operators relevant to this Chern-Simons term are reduced to the only Higgs one. And this is effective operators and given by the normalized by the cutoff scale of this field theory, effective field theory. So, and what happens when we consider time evolution of this Higgs field to explain the isotropic cosmic birefringence? The Higgs field, especially below the electric scale, gets a vacuum expansion value and becomes time independent. Otherwise, so if it drastically depends on time, so it changes the several, the coupling constant or mass itself, then so it might modify the history of universe, especially the recombination epoch of CME. And actually, there's a constraint on the time variation via the electron mass, just like this. So, so it's very small deviation. I mean, and also from the collider constraints. So, so we've never measured this kind of interaction. Then this cutoff scale should be greater than the collider scale, so TB scale. So that's why, so this operator is very, very small. And it cannot explain the reported magnitude of isotropic cosmic birefringence angle. And second, so the dimension 7 operators. So we have the quadratic fermion form. So the operator just like this, and then species electron and neutrino and then Dunk and Upcock. So and they are given by this functional form, the mixing flavor mixing coefficient matrix, and this is a left-handed project operators. Then, so in order, so let me explain. So which will be most promising candidates. First, about electron case. So that should be excluded due to the small number density in the history of the universe. And about neutrino. So I'd like to explain it later. So it's found to be most relevant. So, and about quarks. So also, so we may have a kind of a, the confinement of these quark sectors, but it's stable and time independent after late time of universe. Then, so it should be also excluded. So about neutrinos, so what happens? So the operator for neutrinos written down by this form. So and we just evaluate its cosmological background value. So cosmological neutrino background. And we just evaluate these functions given by the momentum integrations of this ratio and number density. And this is so this is identical to 0. So and at the last scan surface, we have the following expressions for this function. So it's given by the ratio of neutron mass over a temperature of the last scalar surface and the number density. And usually, so it's redshifts, function redshifts. That's why comparing to the time at present time, the time of last scattering surface, the number density is much bigger. Then, this function evaluated at the last scattering surface is dominant for the rotation angle. But it's found to be very small. So then, so I mean, so it's normalized by around the order of 10 to minus 2 degree, but assuming this mass and temperature is small, then this cutoff scale should be above to the 10 to minus 2 GeV to the 10 to 2 100 GeV from the inelastic neutrino scattering process experiment or something. So in any case, in the case of neutrinos, so it also cannot explain the reported isotropic cosmic birefringence angle. Okay, so at the dimension 8 next, it's given by the square of field strength tensor. So this is operator form. And the species is electromagnetic and weak bosons and gluons. In the case of background magnetic field, so we can separate it into the background component of magnetic field and the perturbations. And the components of these combinations can lead to the inner product of electric and magnetic field parallel to the background vector term. So due to this process, it provides the spatially dependent cosmic birefringence angle. So we are interested in, so we have to predict the isotropic cosmic birefringence angle, but not only isotropic, but it also predicts the anisotropic, spatially dependent cosmic birefringence angle at same order. So that's why this is we can say it's not consistent to explain the current measured value. And also this cutoff scale should be much greater. So that's another reason. In other case of weak bosons, for instance, so it's unstable. So that's why, so it's not consistent with the birefringence stuff. And also the gluon condensate, so scale, so so that would be much smaller also than the cutoff mass scale. So in that case, over the TB scale, that's why it also should be excluded. And for dimensions over 8, so so it's given by the previous, the lower dimensions building blocks. That's why that would give a subdominant effects, and that should be also excluded. So in any case, so in the case of a SMEFT, so we showed, so it's impossible to explain the cosmic birefringence angle. So that's why we may need beyond the SMEFT or beyond LEFT. And so other than axiom, so we may consider new particles with the Chern-Simons operators for scalars or fermions, just like this. And also in the presence of these operators, so let me evaluate the resultant cosmic birefringence angle. So first of all, we have to evaluate its cosmological background, but it's bounded from above by the energy density, just like this. Then, so we can assume this energy density is bounded by the critical energy density at the last scattering surface. Then the resultant mass is less than these values for scalar and for fermions. So normalizing by the measured cosmic birefringence angle. So it means, so if we need another new particles, other than axiom, so the mass should be much, much smaller than order of electron volt. And the similar argument would be also applied for the vector field case, dark photon case. And also, so here we focused on the scalar types Chern-Simons operator, but potentially we may introduce a vector type Chern-Simons operators. It's coupled to the vector current to the Chern-Simons sector, just like this. But usually, so so it's a gauge potential, so it doesn't respect the gauge symmetry. That's why if we introduce it, we may introduce another such as Stuckel-Belk field to support this gauge transformation. I mean, to protect the gauge symmetry. But so assuming that, so we can get this operator form. so relevant to the cosmic bias angle. And so due to the relationship between this time derivative of this coefficient, it's given by this Hubble parameter times the original coefficient. So, and for instance, Newton background we assume. So due to the enhancement of this inverse of Hubble parameters, it's possible to realize the order of 0.1 degree the current measured isotropic cosmic variance angles magnitude from these vector type operators. By the way, so we may also allow the photon mass sector, but so it's a there's a lower bound on the photon's mass. That's why so we have to also assume this constraint of the photon's mass. So okay, so let me summarize and give some outlook. So now we have the measurement of the isotropic cosmic variance angle. Sorry, it may give us a hint for new physics, such as actions. But so we asked, is it possible to explain it without using a new field, but by standard model? And actually, the SMEFT or LFT is a powerful tool to systematically list up such operator candidates in the context of the standard model field and its extension. But the standard model fields, the SMEFT or LFT, are impossible to explain the current measured angle of isotropic birefringence. So it might be necessary to think of a new light field. So yeah, that's all. Thank you for your attention.
Thank you for the nice talk. Any question from the audience? Please unmute yourself and ask. If not, I have one small question. That is, so other than considering all kinds of interesting operators that you show for FF tilde, have you considered interactions with gravity? Like, for example, with gravity, I can also write RR tilde, right? So can those curvature terms, Ricci curvature terms of RR tilde can also source such birefringence?
Yeah, thank you. Thank you very much for asking. So, okay, so yeah, so this talk, we mainly assume the axiom, but so from the point of alternative theory of gravity, so it also predicts the cosmic birefringence stuff. For instance, assuming the Lorentz violating theory, so assuming the kind of a unit vector coupled to the Chern-Simons interaction, it also predicts the isotropic cosmic birefringence. And actually, it's a work by the originally, I think, Carroll et al. So, but about the RR tilde, so usually we need coupling of parity violating stuff and the photons to explain the polarization rotations. So, but in any case, so other than action, so the gravitation theory, such as a Lorentz violating scenario, for instance, could potentially explain the isotropic cosmic birefringence.
So no, so what I was wondering was that if you write down a term R tilde, if you have, let's say, standard model photons, even if you do not write an explicit term, they couple to each other at the background level, right? There is a root over G sitting in the metric. So even if you do not write down explicit, how to say, tree level term, because of the root G, you still have couplings via the background to R tilde to the standard model photons, I believe.
Okay, so you mean the RR tilde predicts kind of, okay, so the RR tilde itself predicts difference between two heritage of tensor modes, and then so that tensor modes also predicts difference of I mean,
yeah,
okay.
Yeah, shouldn't it? That's what I'm curious. Shouldn't it? Over G.
I see. Yeah, thank you for asking. That's I think a good point. So, so in that case, so let me see. Yeah, but so sorry, I don't have a strong answer for now. But yeah, let me think about it. Thank you. So I may let you know if I have some ideas. So yeah, thank you.
Okay, sure. Yeah. Any other question from the audience? Please unmute yourself and ask. Okay, if not, let's thank the speaker one last time. Thank you for the nice talk and the overview of many different kinds of interactions that can lead to cosmic birefringence. Will you be able to send us your slides for our seminar?